This is Process Capability Example A. If you would like to see a file of this information, that is contained as an attachment in ReggieNet under the announcements section. Alright, here's the data. We're taking 5 measurements an hour. You see that there's not an R chart. We're assuming you already did the SPC chart and everything looks fine and nothing is sticking out as being a problem. So we don't really need the R for doing this part, so I just kind of left it off. Let's jump over to the answers. Of course, the X bar, the average of these numbers, same as in the SPC chart. X bar, the average of these averages. As I said in the SPC chart examples, this is just a random number generator. It has nothing to do with you. Alright, when we're looking at CP, before we look at CP, we need to jump over here and take a look at sigma. When I talk about sigma, you see this formula up here. It's called standard STDEV dot S. There's one that's called STDEV dot P. We don't use that one. We use the .S one. It's really because we're taking a sample, not the entire population. We're just taking a sample. So you use that formula equals STDEV.S, and we just highlight all of these numbers, not these numbers, just all of these numbers. That's what's in that standard deviation. So again, equals standard dev.s, and then we just highlight all of these, and that will give us a standard deviation of our measurements. So, and you say, well, that says sigma. Well, sigma and standard deviation for our purposes are just two names that mean the same thing. Okay, so let's jump over here and do the calculations for CP. And CP, all we do is we subtract the two engineering specifications. So 17 minus 16, of course, is going to give us 1. And there's that part right there. Don't worry about the dollar signs. That just has to do with absolute referencing. So we take the difference between these two of 1, and we divide it by 6 times sigma, or the standard deviation, to come up with a number. This one is 0.54. Also, I should tell you, in chapter 9 near the end, there are a few examples of it on calculating the CP and Cpk. There's also an example in the chapter 9 notes as well. Okay, and I think there's a video as well. All right, Cpk. Well, the Cpk, before we do the Cpk, it really looks at calculating these two other Cpk values, and we will take the lesser of these two, the worst case. And so before I jump to this one, let's jump over to this one. This one ends up being, we take for the Cpkl, we take the X bar, the 16.6, and we subtract the lower specification limit. So 16.6 minus 16. And you say, well, which way do I go? Well, in most cases it's going to be positive. There's a few exceptions, but to take 16.6 minus 16.0, and you have that number, and then you take that difference and you divide it by 3 times sigma. Okay, so 16.6 minus 16, take that number and divide it by 3 times sigma, or standard deviation. Okay, that's the Cpkl. Cpku, you will take the 17, the upper specification limit, minus 16.6, and you divide that by 3 times the standard deviation. And there you have it. And so you say, well, I have two numbers. Well, think about it as the 16.6 is closer to 17 than it is to 16. So that's going, whatever the upper one's going to be, the problem, the worst case scenario of the two. And when we look at the two numbers, we find that that actually is the case. The 0.43 is the number we go with, the minimum of these two. As you see, that's what shows up over there. So also remember X bar is right there as well. All right, moving along. It says answer these questions. Is the process currently capable of producing parts to specifications? Capable. We are not saying whether it is producing it in the sample, okay? Remember there's a thing that says are there anything that's out of specifications? We are not taking the entire, we are not measuring every single part that comes off the line. So we basically use statistics to project what considering all the variation, and we can basically predict if there's a certain percentage of parts that are going to be out of specification. So in the example we didn't have any, but theoretically there's other that's only maybe 5 measurements every hour, but we could be running 500 parts an hour, for example. So we're just taking a sample of it. So it says, is a process currently capable of producing parts to specification? That's referring to the CPK. No. And this is what you'd say. The CPK is 0.43, which is too small. And you say, well, how big does it have to be? I'm going to tell you in just a second. To meet specifications, the CPK would need to be 1.0. It would be better if it was at least 1.33 to give us a little more room for process variability, just shifts in the process. So that is the answer to that particular question. You're going to talk about yes or no, and then you're going to say the CPK is too small or too big or just right, or not too big, it's good or it's too small. And then you're going to talk about it needs to be 1.0, and you're also going to say it should be better if it was 1.33. That's what your answer should look like. Okay. Next question is, if the process was perfectly centered within the specifications, would it be capable, capability, would it be capable statistically of producing parts to specifications? And as soon as we hear this word, if the process is perfectly centered within the specifications, if you take the CPK and you center it perfectly at 16.5, which is halfway between these two, if this was perfectly at 16.5, this would have a CP of 0.54. Let's just pretend that it is at this point. I'm just going to put in 16.5, and look what happens. CPKL 0.54, CPKU 0.54, CPK, these are both the same. Okay, see how that works out? I just put it back to the way it was. Okay. The CP value is the measure of how our process would perform if it was perfectly centered in the middle of the specs, the engineering specs. You need to write that down on your exam. In our case, the CP was 0.54, which is less than the needed 1.0 to produce all parts to spec. So we need at least a 1.0 on that in order to make it work. And you could also have the verbiage about needing to be at least 1.33, but I'm really looking at it, you covering your tracks at least once in these two things to talk about the 1.33. Okay. And it says using the CP values in B4, well, it's actually this is supposed to be B4. Using the CP value in B4, which again is 0.54, what would the CP be if the specifications were doubled, twice as wide? Well, if you make it twice as wide, think about going from 16 to 18, that'd be twice as wide, right? Well, so all it does is all you do is just making that width twice as wide. So all you really have to do is multiply it times 2. Multiply it times 2. So 0.54 times 2, the new CP would be 1.08 if the engineering people allowed us to double the specification to, let's say, 16 to 18 ounces. All right, next question. using the CPK value in B4, which we talked about, and that would be the 0.43. Actually, it's going to be the 0.43. What would the tolerance or engineering specifications have to be in order to obtain a CPK of 1.0 on both sides of the specification? 2 decimal places. And this one looks a lot more like I don't know what to do type thing, but if you go down here to this formula, the CPK L, in order to calculate the lower specification, you're looking at this one. I'm going to make it nice and bold so you can see it. Is the lower specification, you take X bar bar minus the desired CPKL, and it says our desired CPK is 1. So what we're going to do is we're going to say X bar bar, which is 16.6, and we are going to do minus the desired CPK lower, and we want that to be 1. That's what we said right here. We want a CPK of 1 times 3 times the standard deviation, which is right there. You plug that formula in and you end up with the lower specification limit. If you could fix things, would be 15.68. To do the upper specification, it's somewhat similar. This one was X bar bar minus CPKL. This is X bar bar plus CPK for the upper side times 3 times standard deviation. Well, we still want 1. That's what it's saying right there, 1. And we're in times 3 times that standard deviation. So if you plug those numbers in, you're going to come up with 17.52. Again, you can pull this up in announcements and see the formulas and kind of trace them out to see how it works. Now, this is something I've added. It's not in the current exam sample, but I may choose to include it on the actual group exam, so be prepared. Using the CPK value, whatever, what would the tolerance or engineering specifications have to be in order to obtain a CPK of 1.33 on both sides of the specifications to do 2 decimal places? Well, guess what? This formula is going to be very, very similar. We're going to go back to this one, and we're going to say lower specification limit is going to be X bar bar, which is 16.6, minus our new desired CPK that we would like to see, and that would be 1.33, not 1 like in this one, 1.33 times 3 times standard deviation, and you'll come up with this number. And you see it, I have the 1.33. I just didn't put it where it's supposed to be. I just kind of tagged, just kind of put it on the end. And for the other side of the specification limit, the desired to have a CPK of 1.33, you would say X bar bar plus 1.33 times 3 times standard deviation, which we said was 0.31. And you're going to come up with those numbers. You notice that this is wider than this one, because for us to be more capable with just changing the specifications and not improving the process, that you're going to have a wider specification to be able to operate like you want to.